Hello and welcome to this series of screencasts about the role of mutation in evolution. The topic for today is an emerging critique which says that there's a classical neo-Darwinian view of evolution that treats selection as the only source of direction because it assumes incorrectly that variation is isotropic, meaning that variation spreads out evenly in all directions with no preferences or tendencies. What I'll do today is to begin with a 3 or 4 minute synopsis of what this argument gets right and what it gets wrong. And then I'll give a longer version with more explanation and documentation. And those of you who watch my screencast know that my arguments will be properly sourced so that you can replicate them for use in scholarly work. Okay, so let's begin with a brief review. What this isotropic variation critique gets right is that indeed in the history of evolutionary thinking, neo-Darwinism is a school of thought that differs from every other traditional school of thought in asserting that selection is the only source of direction or non-randomness, whereas variation is merely a source of random raw materials and doesn't play a dispositional role. So here, Ernst Mayr, in a volume on the so-called evolutionary synthesis, labels this school of thought Darwinism. And here we have a more contemporary source, Ridley's entry in the Oxford Encyclopedia of Evolution, which refers to this as the theory of natural selection. And he says that in this theory, the processes generating variation are not the same as the process that directs evolutionary change. He says that, by contrast, every other traditional school of thought, Lamarckism, orthogenesis, mutationism, saltations, variation plays some dispositional role so that one has to understand how variation works in order to understand how evolution turns out. So that's what the critique gets right. What the critique gets wrong is that this position that Mayr and Ridley and others are taking was never based on assuming isotropic variation. Instead, Darwin and his followers argued repeatedly that the details of variation are irrelevant to how evolution turns out, because selection governs evolutionary change. So, suppose that every trait varies a little bit up or down, then selection can do whatever it wants. It has the fuel to go in any direction, regardless of whether there are some tendencies of variation. And this neo-Darwinian position has been justified in many different ways. We'll go through all these arguments. Darwin argued that there are laws of variation, but they're irrelevant to how evolution turns out. Fisher said once you understand how population genetics works, you can ignore the causes of mutation and just focus on selection because mutation is a weak force. Mayr said that populations have such infinite variability that selection can create almost any shape. Dobzhansky compared evolution to statistical physics and said that mutations happen in individuals. They happen at the wrong level to be determinative as statistical forces. So they're just irrelevant as the motion of an individual molecule in a gas. So basically, neo-Darwinism plus isotropic variation is neo-Darwinism, and neo-Darwinism plus anisotropic variation is neo-Darwinism. So this isotropic variation critique is historically unfounded and gives us the wrong impression. Indeed, when Darwin's followers say that variation is a random or chance factor in evolution, they often qualify this by saying, oh, we're not saying that mutation is uniform, only that it's irrelevant to how evolution turns out. So where does this leave us? It leaves us with a lot of wrong claims. The isotropic variation critique is basically wrong, but also all of these claims are wrong. So those of you who follow my work know that mutational and developmental biases in the introduction of variation can be causes of orientation or direction in evolution, and this is well established theoretically. Empirically, we know that ordinary mutation biases strongly influence what happens in adaptation. So the real issue for reform going forward is to understand why these arguments are wrong. And so the main focus of this talk is going to be documenting these arguments and explaining why they're wrong. Okay, so having finished this short review, let's consider these issues at greater length, beginning with what isotropy means and why it's a useful term. So in biology, we don't hear these terms isotropic and anisotropic very often, but they're perfectly good terms used widely in other areas of science, particularly material science, but also cosmology, where there are big questions about whether the universe is isotropic or homogeneous. So isotropic materials, like most glasses and metals, look the same no matter how you slice them, or to say it in a different way, measurements look the same along any dimension. By contrast, if I give you wood is not an anisotropic material. If I give you a piece of wood, you'll know how it was oriented relative to the growth of the tree, because the tree rings, if you slice longitudinally across the across the vertical axis of growth, then you see concentric rings. But if you slice radially, then you'll see the growth rings as parallel lines. So it looks different depending on how you slice it. Distinctions like isotropy and homogeneity can be made on different scales. All right, so a material could be homogeneous or isotropic at one scale and then different at another scale. So, for instance, and homogeneity and isotropy are not the same thing. So on the left we have a material that is homogeneous on the scale of this image. All right, if you look at one chunk of it or another chunk of it, it looks the same. But it's not isotropic. There's clearly a direction this way and this way. And most crystals are like that microscopically. They have a particular growth orientation. Well, on the right we have a figure that's isotropic if we consider the center point as a reference point, but it's not homogeneous because the lines get more sparse as we go out from there. So referring to an isotropic cloud of variation, which is what Gould originally did, is actually a kind of reasonable null model for variation because extreme variants aren't as common as modest variants. So this terminology of isotropic variation now appears importantly in arguments from Ivo Devo and from extended synthesis reformers who are drawing attention to the role of generative processes in evolution. So I'm going to cite two key sources for that. Remember, part of the point here is to document where these arguments are coming from. Excuse me. So in this article, the focus of Scholl and Pigliucci is the use of Ernst Mayr's proximate ultimate distinction by Ernst Mayr and by Bruce Wallace and others in the 1980s and 90s to argue against the relevance of development to evolution, undermining Ivo Devo claims about how development shapes the course of evolution by shaping variation. And they say here in this article that Mayr and others who make this argument are implicitly assuming isotropic variation. Another recent source is this paper from Salazar Ciudad and Cano Fernandez. The authors seem to assume, contrary to neo-Darwinism, that tendencies of variation must be important in evolution, and this is why they conclude that in the modern synthesis, variation is assumed to be isotropic. And if we look at this paper and read it closely and we ask, well, where are they getting this idea that this is what neo-Darwinians believe? They're actually not citing any neo-Darwinians. They're citing Per Ahlberg and an earlier paper by Salazar Ciudad. And in fact, Salazar Ciudad says in that earlier paper that this is not an explicit claim of neo-Darwinians. That is, you can't catch the neo-Darwinians saying that they assume isotropic variation. He's saying it's implicit in their arguments. And this term isotropic variation actually comes from Gould's 2002 book, but I would argue that he's actually saying something that is more subtle and defensible in this passage. I won't read out the whole thing. I just want to draw your attention to the way he uses conditional language, and he says, if change occurs, reading up here on the upper right, by a long and insensible series of intermediary steps, then, under these provisos, variation becomes raw material only an isotropic sphere of potential. He's really getting it right when he says, under number one here, if nothing about the provision of raw materials imparts direction to evolutionary change, which is saying something different than saying there are no directions in the material. And Gould also does not criticize this position for being naive, so I think Gould understands the neo-Darwinian position, and he's just stating things a little bit in a misleading way here. Okay, so I've reviewed what some of these critics of this classical position argue. What about what Darwin and his followers say? Because it's best to let them speak for themselves rather than to ask critics like Per Ahlberg, what's the basis of neo-Darwinism? So let's go back to the ways that leading advocates of neo-Darwinism have argued that the details of variation are irrelevant to how evolution turns out. I showed this table before, so I'll go over this list in detail, but I want to emphasize two things first. So this kind of argument is characteristic of neo-Darwinism. In every other school of thought, variation has some dispositional role in determining the course taken by evolution, so it's important. So if we want to understand neo-Darwinian thinking, it's important for me to present that to you sympathetically, so I'll spend a few minutes on that. And secondly, as I stressed before, each of these arguments is wrong because we know that variation can be dispositional in evolution. And we need to understand why that is. And for those of you who want to read further, these arguments about the irrelevance of variation to evolution are reviewed in Chapter 6 of my book, and in Chapter 8 there's a theory about that explains the connection of how variation can be dispositional. Okay, but let me first explain this to you in a sympathetic way. The first example I would give is this example of a sandcastle here. So the sand in this example is merely a material cause. Okay, a material cause is a source of substance and not form. So, for instance, Aristotle explained in different ways this distinction. One of the ways was to describe the making of a statue, and in the making of a statue there's a mold which provides the form, but the substance comes from the bronze that's melted and molded and poured into the form. All right, but that provides substance only. It provides the mass and the specific density. It determines properties like that, but it doesn't determine the shape. The shape comes from the mold. And likewise here, the shape of the sandcastle comes from this form. So if we want to explain the shape of the sandcastle, our explanation focuses on the mold and not on the sand. Okay? And importantly, if we were to take this sandcastle apart and look at each individual sand grain is different and has a different shape. And each individual sand grain has a millions of years long history that we could write a big book about, every single sand grain. But we don't, those are irrelevant details. We don't need to tell those stories. We don't need to say each sand grain is distinct, because each sand grain plays an arbitrary, anonymous role in explaining the shape of the sandcastle. Okay, so again, this is what a raw material is. This is what it means to be a material cause. All right? So if we think of variations like the sand grains, then they would be like raw material. And if we think of selection as the mold, that would be like the formal cause. Another way to explain this neo-Darwinian position is with something that I call the morphotron. So the morphotron is an imaginary device. It just helps us to think a little bit more clearly for creating shapes. And for every detail of the shape, like consider the tail, like the length of the tail and the thickness of the tail and the profile of the tail, there's a dial for each of those little features that we can use to change the shape subtly. And if we suppose that there's enough dials on this morphotron, then we can imagine changing the shape, any shape into any other shape, like the shape of an alligator into the shape of a horse. And it helps us to think about evolution in the sense that if selection is the hand on the dials of the morphotron, then selection is responsible for determining this shape. And it allows us to understand the argument that if there's just a little bit of variation in every trait, if we can turn everything up and down a little bit, then maybe selection is wholly responsible for the shapes of things. All right? So I'm giving you this explanation because I want to make it clear that this neo-Darwinian position is not inherently irrational, it's not inherently unscientific. It's been a very important view because it does allow us to make explanations for things very easily just by positing abundant variation and the hand of selection on the dial of the morphotron. All right, but let's go back to these arguments now in more detail to document what Darwin and his followers said and why each argument falls apart ultimately. Okay, and the examples that I cite, there's a lot of examples in Appendix D of my book of these irrelevance claims. All right, but let's begin with Darwin's argument, based on his extended analogy with the builder. So Darwin's argument is like the sandcastle argument, except instead of sand grains, they're these stones that fall from a cliff. And Darwin imagines a builder that builds like a castle from these stones. He calls it, in one of his versions of this story, a noble edifice. So here's a noble edifice. This is Rochester Castle near London, built in the 12th century. And these are uncut stones that it's built from. And Darwin emphasizes when he explains this, he says that the stones fall from the cliff, and that reflects natural laws. Because Darwin believed in a law-like universe, and he said the same thing about variation. He didn't claim to understand where variations come from, but he believed that they followed natural laws. And he emphasizes how the builder chooses the stones. And from an infinitude of shapes. There's like a giant infinite field, infinite scree field here of stones. And Darwin concludes that the laws that determine how the stones fall from the cliff bear no relation to the structure that the builder builds, and in the same way, the laws of variation bear no relation to the structures built by natural selection. Now, before considering what's wrong with this comparison, let's consider another metaphorical argument. So Gould, in his book of essays, Ever Since Darwin, has this essay called, I think it's Darwin's Untimely Burial, where he describes how all of the architects of the modern synthesis compared natural selection to an artistic creator. So Darwin's comparing natural selection to this builder or architect. Dobzhansky and Huxley and so on compared natural selection to an artistic creator, and Gould lists some of those comparisons here. So selection, this dichotomy is fleshed out by these comparisons. Selection as the painter, variation as the palette of pigments. Selection as Shakespeare, variation as the words in the dictionary. Selection as a sculptor, variation as the stone, selection as the potter, variation as the clay. If we think about the role of variation in evolution that way, it's kind of difficult to think about how raw materials or the artist's materials would affect the outcome. And we might come up with something like this. I like this example. So for Washingtonians or those who are fans of the Washington Monument, you might have heard this story, or you might have noticed that if you look about 150 feet up on the Washington Monument, the stones change color. And the reason is that construction was halted at one point in time, I think it was 1808, and when construction resumed, there was a new source of marble, and it was slightly different from the previous marble, slightly different in color. But these are cut stones. The stones are still being cut according to a plan, and the building is kind of going up according to a plan, and so it doesn't really make much difference what's happening there. So what's wrong with these metaphors as guides to thinking about evolution is that they assume way too much abundance and way too much determinism in the choice that's driven by some prior design. Okay, if we live in a finite world and evolution is a stochastic process, things are going to look different. If we're building something from these fallen stones over here, the builder is not going to spend the next 6 months, even if the stones are infinite, we're not going to spend the next 6 months or the next 5 years digging through every single stone to find the perfect stone to put down next. We're going to grab what's near at hand. What's near at hand is going to be the stones that are on top. The stones that are on top are the ones that have fallen more recently. Okay, so we're going to have this recency bias, for instance. And the path of evolution, like the shape of the building, it's not predetermined. The way to understand mutation-biased evolution is that in a multidimensional space, there are many different ways to go up, and so evolution tends to go up in mutationally more favored directions rather than mutationally less favored directions, and the result of that is that the trajectory that is taken by evolution, including adaptive evolution, has both fitness dimensions and dimensions that reflect biases and variation. And the way to think about this in terms of population genetics, in terms of the choice exercised by selection, is that the classic way of thinking in the modern synthesis is that variation is like this buffet. I'm comparing two different self-service restaurants here, the buffet and the sushi conveyor. And in both cases you make choice, but the choices are different. All right? The buffet model, in the buffet model of the modern synthesis, there's infinitely abundant variation, and you choose exactly the right amounts of each thing to make the perfect plate. In the sushi conveyor restaurant, you don't choose what's coming by. You don't choose when it's coming by. It's just that at that moment, you get to say yes or no. You're still exercising choice, but it's a different kind of choice, and it has different implications. Okay, let's go on to the next argument, which is this argument about levels from Dobzhansky. So Dobzhansky and colleagues. So in their 1977 textbook, Dobzhansky, Stebbins, Ayala, and Valentine, they're making an argument by analogy with the gas laws of physics, which is something that Fisher did. So what they're saying here is that each unitary random variation is of little consequence and can be compared to the random movements of single molecules within a gas or liquid. Okay? The directional force of evolution, they say, comes from these mass action forces that act in the population, all right, not from individual movements of atoms. And this argument was repeated here. I've shown a couple of cases here where Dobzhansky was using this argument. He used it over the course of many decades. So what's wrong with this argument? Well, first of all, the first problem with this argument is that biology and evolutionary biology does not have levels like physics with vastly different sizes and qualitatively different behavior. You can point to like cells, tissues, organs, organ systems, individuals, demes, populations, and people will often be able to tell what you're talking about and distinguish them, but they don't have vastly different sizes and vastly different behaviors. Some large cells are larger than small organisms. An average ant weighs about 3 milligrams, and so a population of 1 billion ants weighs 3,000 kilograms, which is about what an elephant weighs. Okay? So these are not vastly different scales. They overlap. And I'll direct you to, this figure comes from a book by the philosopher William Wimsatt. I'll direct you to his work for a further explanation for that. I want to make a more evolutionary point about this in regard to population genetics, excuse me, which is that this appeal to gas laws doesn't just require very large populations. It requires that evolution depends on quantitative changes in traits affected by arbitrary large numbers of loci. So this is what we'd have if we were doing a model of evolutionary quantitative genetics. The trait value reflects the contributions of an arbitrary large number of loci, and so it never matters if one locus happens to mutate to increase the trait value versus decrease the trait value. That doesn't matter because there's thousands of other loci that are doing different things. All right? But in any other case, it can matter in evolution whether mutation at a locus goes in this direction or in this direction. That's why in his textbook of molecular population genetics, Matt Hahn says, all of evolution begins as one mutation on one chromosome in one individual. And it's also why evolutionary geneticists have concluded rather definitively that we have to treat the introduction process in order to get the dynamics of evolution right. We can't really use this physics approach that Dobzhansky was recommending. And this statement, I want to say in passing, by Hahn sounds very commonplace, but this is something that architects of the modern synthesis would never, ever have said. Okay? For Dobzhansky, Meyer, and so on, selection in a population is conducting a symphony and all the sections are playing at the same time. All right? It's complex and interactive. There are many balls in the air at the same time. It's not just, again, a symphony. It's not just one note begins and ends, and then there's another note over here, and then there's another note over here. All right? It's many loci, allelic variation at many loci being mixed together and shaped by shifting gene frequencies. Okay, getting back to our list. The next two arguments here are about the gene pool and the idea of infinite or inexhaustible variability. So based on what I've said so far, we already have a basis to understand what's wrong with this argument. So Darwin and Fisher and Dobzhansky, they're just imagining a world that's far too deterministic and idealized in favor of selective choice. So here's an example of the gene pool argument from Stebbins or from that textbook by Dobzhansky and colleagues, and they're saying, we're not going to see an influence of the mutation rate on the rate of evolution because there's so much abundance in the gene pool. All right, and this is really just a hand-waving argument, and it doesn't really work out. And it's the same problem with this argument from Meyer, where he's saying infinitely variable natural populations are of such evolutionary plasticity that natural selection can mold them into almost any shape. Except here, I think the breakdown of this logic is much more interesting and hasn't received enough attention because we have a class of mathematical models in population genetics where variation is literally infinitesimal and inexhaustible. Those are the models of evolutionary quantitative genetics. And in this formalism, there's a formalism for the short-term change in trait values, that's delta z bar, and it's equal to the matrix of variances and covariances multiplied by this beta vector of selection differentials. And what multiplying this means for a single trait, so there's an example down here at the bottom of changing the expected value for the first trait. There's three terms here, and the first term is based on the variability in trait 1 and selection on trait 1, but the second two terms are based on the covariation of trait 1 with trait 2, or the covariation of trait 1 and trait 3, and selection on those traits. All right? So there's this indirect effect. And what that means relative to the morphotron is that you can imagine that selection has its hands on the dials of the morphotron, but changing one of the dials causes other dials to turn in an unsolicited way that's dependent on what's happening inside the black box. All right? So, again, quantitative evolutionary genetics is the closest thing that we have to a mathematical formalism of this Darwinian thinking that says that there's inexhaustible infinitesimal variation, and so selection can do what it wants. But the formalism doesn't say selection can do whatever it wants. It says that the rate and direction of evolution are jointly determined by G and by beta. And what this means is that we can't really have a theory of evolution without knowing what's inside the black box. You can't ignore that. And selection can't be this creative governing force that was imagined. So the morphotron is an impossible machine, in the same sense that a perpetual motion machine is an impossible machine. Okay, down to two more claims on this list, the weak force claim and the approximate ultimate distinction. I'm going to spend considerably more time on this weak pressure claim because it has more substance to it. It's based on an argument from a claim of causation that comes from population genetics. And so here we see examples from the earliest days of the synthesis through the 20th century. Authors as diverse as Huxley, Ford, Gould, many others have rejected the possibility of evolutionary directions due to internal tendencies of variation based on the argument that because mutation rates are small, mutation is a weak pressure, meaningless relative to the much stronger force of selection. Now again, this argument is wrong because biases in the introduction process continue to be important no matter how small is the mutation rate. So how do we think about what's wrong with this argument? So one way to think about it is that the argument seems to treat evolution as a zero-sum game in which either selection or mutation has to win, whichever is the bigger force. But as I said earlier, the way to think about this problem is that evolution is happening in a multidimensional space, and there are many ways to go up, and so you can both have upward directions that are beneficial and directions that are mutationally favored. But we also have to ask, but that's a very abstract criticism, we also have to ask what makes this wrong in terms of population genetics, because this argument actually emerges from a specific model from Haldane and Fisher, which was the mutation selection balance. So they began by trying to understand why don't genetic diseases just disappear from the population given that selection is powerful? And the answer is a sufficiently large population is going to converge on an equilibrium value where recurrent mutation is pushing up the frequency of this disease damaging effect like hemophilia, and selection is pushing it down. All right? And in the simplest case, that balance point is just mutation rate divided by selective disadvantage. And this expected frequency or equilibrium frequency is a small number, much closer to 0 than to 1, because mutation rates are so small. Now, Haldane and Fisher both derived this result, and they generalized from this that mutation was a weak pressure and was unlikely to be an important source of direction in evolution. Haldane stated this in his 1927 paper and repeated it in his 1932 book and his 1933 paper on recurrent mutation. Fisher's conclusion in his 1930 book was much more dramatic. So here he's in the first section here. This is from the first chapter of his book. He's kind of setting up this example where there's a mutation that's 1 in 10 to the 5th, and there's a selective disadvantage of 1%, and the equilibrium expectation is 1 individual in 1,000. And he goes on from there to say, for mutations to dominate the trend of evolution, it is thus necessary to postulate mutation rates immensely greater than those which are known to occur, and of an order of magnitude which in general would be incompatible with particulate inheritance. And he makes an even more general statement here about how this is kind of a necessary consequence of particulate inheritance, and then comes back to the issue again later in the chapter with an even more forceful argument that's more practical, because he's saying we have to set aside this whole group of theories which ascribe to hypothetical physiological mechanisms controlling which mutations happen a power of giving directions to evolution. And he says, the investigator who knows this, down here in the last sentence, if you understand population genetics, he's saying, then you'll focus on selection because these details of mutation aren't determinative. And Fisher's argument was repeated by many others. You notice, if you remember going back a few slides to that quotation from Huxley, he's very much echoing Fisher's argument. And notice that this argument is completely general. He's talking about any kind of effect on mutation. So he doesn't use the word mutation bias because it didn't exist then, but it covers that possibility. And in fact, this argument played an important role. So in this paper from Provine in 1978, the paper is called The Role of Mathematical Population Geneticists in the Evolutionary Synthesis, and he's kind of responding to a challenge from Ernst Mayr, who said that he didn't think population genetics did very much for the synthesis. And Provine says, well, here's one thing that it did. It showed people how to think of the sizes of forces, and one of the conclusions was this conclusion about selection being powerful and mutation being weak. Okay, so I've explained this argument in great detail. What makes it wrong as population genetics? Well, the simplest way to explain it is that the influence of biases in mutation does not come from this mass action pressure. It comes from biases in the introduction process, and Haldane and Fisher just didn't consider that. They tended to assume that evolution was shifting gene frequencies in a gene pool. And that's a general feature of classical population genetics. Origin fixation models are very familiar today, where we treat evolution as the product of mutation, rate of origin and probability of fixation, but those were not introduced into theoretical population genetics until 1969 in response to the molecular revolution. So what Haldane and Fisher are doing is they're really thinking about mass mutational conversion of the population, right? That's the possibility that they're really looking at. So here's a simulation from John McDonald's, a teaching tool from the population geneticist John McDonald. And it's showing a simulation over 100 generations of a small population, and he's turned down the reproductive variance to 0. So every individual just leaves one offspring in the next generation. So there's n different lineages here. The conversion from the red allele to the blue allele takes place by recurrent mutation at a high rate. So if there's n alleles in the population, there's n allelic lineages, and it takes n events of mutation. Okay, it's a process of mass conversion rather than replacement. So this is not drift, this is not selection, there is no drift, there is no selection. This is what evolution by mutation pressure looks like. Another way to critique this argument from Haldane and Fisher is their use of forces reasoning, because they reached a wrong conclusion about forces because of this assumption of standing variation. So for instance, Fisher compared this, in the example that I showed you, Fisher compared this mutation rate of 10 to the minus fifth and the selection coefficient of 1% and said, oh, well, that's much larger. But that logic only applies if you're talking about movements in the interior of an allele frequency space. If evolution ever has to jump off the edge of a frequency space into the center, where an allele frequency has to go from 0 to not 0, then selection can't do that at all. Okay? The power of selection to do that is 0. And so the power of mutation to do it, even if mutation rates are low, is infinitely larger than the power of selection. But Fisher wasn't thinking about this kind of movement. And in fact, there's a whole body of population genetics literature that doesn't deal with mutation, just treats evolution as shifting gene frequencies. So I like to pull out this book from Anthony Edwards, who studied with Fisher. It's got hundreds of equations in here, but there's no mutation rates. There's not a single mutation rate anywhere in this book. A book of population genetics. And this is a very general problem with classical reasoning, and I'll return to some implications of that at the end. Okay, finally, the proximate ultimate distinction from Ernst Mayr. I don't know why this argument gets so much attention. It seems utterly empty to me, merely a reification of Mayer's kind of impoverished view of evolution. He's just declaring that selection is the ultimate cause, and ultimate causes are important things, and the other causes are proximate causes that you study in functional biology, not in evolutionary biology. He's basically saying evolutionary biology is about ultimate causes are selection. This other stuff is not part of that. And what's important is the way that Meyer and others use this argument against claims of novelty from evo-devo. So that was the topic of that piece that I mentioned earlier from Scholl and Pigliucci. They were trying to understand why Meyer rejected a role for development in evolution on the grounds that development is a proximate cause. And that's where Scholl and Pigliucci said this is because of the isotropic variation assumption. But what we've seen is that when the architects of the modern synthesis called on empirical and theoretical results to establish selection as a true cause in evolution, they pulled up the ladder behind them and made it impossible for anyone else to establish a general cause claim, because they sort of configured the questions and the way of thinking about causes to favor selection. So let's think about that more systematically. So one of the things that the synthesis is credited with accomplishing is establishing a unified way of talking about causation. This is the population genetic approach. Causes have to be expressed in terms of population genetics, and if you're going to be rigorous, you have to demonstrate them in populations before you start invoking them. Otherwise, that's unreasonable speculation, and that all sounds good and rigorous. But the version that they offered us of doing this isn't very general. So my favorite kind of causation that I've mentioned before is biases in the introduction process. But none of these criteria that were put in place, it doesn't qualify. Okay? So they defined evolution as shifting gene frequencies in a population. But this isn't, one event doesn't count. It's at the wrong level. It's just like the movement of an atom. They said that causation, so again, what they did was they looked at that selection, and they said, oh, I understand what causes look like. They look like selection. What do? Well, they cause mass action shifts. They cause fixation. They act at the population level. They're quasi-deterministic. But the introduction process, I mean, again, we know that biases in the introduction process are causal, but they're not quasi-deterministic. They're not mass action forces. They don't cause fixation. All right? And they can't be demonstrated in experimental populations of animals and plants. They need a larger time scale than that, or they need to use microbes. And there was even an approach to explanation that was very common in the synthesis era and is still common, where you rationalize what you observe as an end state of some process. And so that, again, suggests determinism, but these mutational explanations that depend on biases in the introduction process aren't like that, okay? So getting back to the big picture and back to debates about evolution and critiques of the modern synthesis and so on, it's a real strategic mistake for reformers like Scholl and Pigliucci to begin their discussion by accepting all of these framings from the modern synthesis, because again, the architects of the modern synthesis pulled up the ladder behind them. They defined the playing field to favor selection with their shifting gene frequencies theory, the forces theory, etc., etc. It makes my head spin every time I see someone talk about the proximate ultimate distinction. It makes my head spin when I see evo-devo articles refer to variation as raw materials. If you believe in the premises of evo-devo, then you don't actually believe that variation is the raw material. It's time to find new language and a new metaphor. Don't use the old ones. Okay, time to wrap up here. Thanks a lot for listening. If you like this lecture, there are more lectures in this series. I kind of have this hypothetical series of lectures here. The ones with check marks are done. There's a lot of stuff that's planned but not done, and you can find those on my YouTube channel. So to summarize, there's this isotropic variation critique that purports to identify a flaw in classic reasoning. Namely, there's this false assumption that variation is isotropic, and this leads to a position against sources of direction other than selection. So it's then it's concluded that selection is the only source of direction, and variation can't be a source of direction. But the argument's not correct. The classic view that denies a dispositional role of variation is not based on assuming isotropic variation. Instead, it looks something more like this. Okay, there's a dichotomy of roles where selection is the potter and variation is the clay, and it's sort of primary. It's not a conclusion. It's more like a premise. And it's justified in various ways, all these various ways that I talked about. So there's this arrow of finding ways to justify this dichotomy, often with hand-waving arguments and metaphors, but also with these more scientific arguments like Dobzhansky's argument by analogy with physics, or the Fisher-Haldane opposing pressures argument. They're calling on population genetics to justify this idea that variation is not dispositional. And the argument that I was just making is this arrow here is that putting in place these beliefs about causation just tends to reinforce this dichotomy and make it difficult to establish anything else. So what's the path toward reform? Not using wrong arguments would be a start. I mentioned raw materials. These arguments from the modern synthesis were presented to us as universal principles of causation to be used generally in reasoning about the causes of evolution. But they're not. They're not universal principles. They're really limited to this neo-Darwinian shifting gene frequencies view, and they don't work more generally. And the problem that we have in evolutionary thinking is it's not that people hate new ideas or never think about new ideas. We love new ideas. But we just can't seem to get rid of the old ones, the problematic ones. And there's too much of a conservative sentiment that wants to just keep using the old theories. And I'm sure this is going to happen with forces. I'm sure everyone's going to just want to continue to use the word forces, even though there's a serious problem with this conception of forces. It doesn't help to clarify anything, in my opinion, to keep the old words, but make them mean something new. If you want to clarify your thinking, get rid of the old words. I'd say, let the past die, kill it if you have to. All right, thank you again. I'm going to scroll through the bibliography.